Okay, so in this video, we will consider an example of linear regression and correlation given the following 6 pairs of data. So here we have two variables, x and y, and the following pairs. So negative 1, 1, 1, 2, 2, 3, 4, 3, 6, 5, and 7, 8. Now, these variables could be any variables. You could assume, for example, that x is at any particular time whether a stock went up or down, same thing for y. So this pair could be at a particular time, stock X went down by $1, stock Y went down by $1. At this particular time, for this observation, stock X would have went up by $1, stock Y up by $2. So we're following at different points in time the trend for the two stocks. So we have our 6 pairs. Now, of course, the question is, does there exist a linear relationship between the two stocks, between the two variables? And if there is, how good is it? So, of course, we will find the linear relationship with the line of least squares. And to measure how good of a linear relationship it is, this will be given to us by the coefficient of correlation. And all we need to compute all of these things is to construct a simple table for the sum of the x, y, x squared, y squared, and xy values. Once we have this table, it will be very straightforward to compute both the line of least squares, so our line of regression, and our coefficient of correlation. So here's the table. So the first column will be for the x values. So let's list them. Negative 1, 1, 2, 4, 6, 7. Column 2 for the y values, and of course the corresponding y values. Negative 1 goes with negative 1, and so forth. 2 goes with 1, 3 goes with 2, 3 goes with 4, 5 goes with 6, and 8 goes with 7. And that's our column for the y values. We need to construct 3 additional columns. A column for the x's squared. So let's square all of these terms, which will give us 1, 1, 4, 16, 36, 49. We have to have a column for the y squares. So square all of these, keep always the same order. 1, 4, 9, 9, 25, 64. And finally, the third column, the cross terms, the product of the corresponding x and y values. So 1 times 1 times negative 1, 1. 1 times 2, 2. 2 times 3, 6. 4 times 3, 12. 6 times 5, 30. And 7 times 8, 56. And now we need the total of these columns. So all we need are the summation of the x terms, so adding up all of the x values, the summation of the y's, adding up all the y's, the summation of the x's squared, adding up all of the x's squared, the summation of the y squared, adding up all the y squared, and of course the summation of the cross terms, the x times y's terms. And we can put these totals at the bottom of our table. And we will signify that we have here the column totals using, of course, the sigma notation. So if you add all of the x's together, you will find a sum of 19. Add all the y's, you will find a sum of 20. Add all the x's squared, a sum of 107. Add all the y squared, a sum of 112. And if you sum the x's times the y's, you'll have 107. And here the fact that the sum of the x's squared and the xy terms are the same is purely coincidental. Okay, now that we have this table, how do we use it to find our line of least squares and our coefficient of correlation? Well, let me move up, but remind ourselves that n, of course, n is not the total number of values for x and y, but n is the number of pairs. And we have, well, if you count all of the x and the y's 12 values, but we only have 6 pairs. So n is equal to 6. Okay, so let's first find the equation of our line of least squares. So if you remember, y will be given by the slope a hat times x plus the y-intercept b hat. Well, let us first find the slope a hat. Now here's the formula given as a function of all of our column totals and the number of data pairs. So here's the formula. It's the sum of the x's times the sum of the y's minus n times the sum of the cross terms x, y, and this is divided by the sum of the x's, but the whole summation squared, minus n times the summation of the individual x's squared. And now if you look, well, everything in this formula we already have computed. We have all of our column totals, we have n, so we can just replace. Sum of x, 19, times the sum of the y's, 20, minus n, which is 6, times the sum of the xy terms, 107, over the sum of the x's, 19, all squared. So 19 squared, minus n, which is 6, times the sum of the individual x's squared, this is this column total, 107. Now you can compute with your calculator the numerator and denominator, and you should find negative 262 over negative 281. And now with your calculator, you will find an approximate value, and here we'll round up to the 4th decimal place, 0.9324. So there we have it. We have the slope of our line of least squares. Well, let us now find the second value, the y-intercept, b hat. The great thing about this is the numerator for b hat is different than for a hat, but the denominator is actually the same. So it is over the sum of the x's all squared minus n times the sum of the x's squared individually. The numerator is different. It is the sum of the x's times the sum of the cross terms, x times y, minus the sum of the y terms times the sum of the x's squared. And once again, everything in this expression is a function of our totals and n, so we can replace sum of x, 19, times sum of xy's, 107, minus the sum of the y's, 20, times the sum of the x's squared, 107, divided by, well, same as before, 19 squared, minus 6 times 107. If you calculate the numerator and denominator, the numerator will be negative 107, which is pretty easy as 19 minus 20 is negative 1, over, of course, the same as before, negative 281. Using once again your calculator, and we'll round up again to the 4th decimal place, a y-intercept value of roughly 0.3808. So there you go. With our two formulas, we have now the equation of our line of least squares. Y is approximately, as these are approximate values, a hat, so 0.9324, 0.9324 x plus b hat 0.3808. So now we have the line of least squares. But again, the idea is once you have the line of least squares, you would like, if possible, to use it to make predictions. So if you knew the x value, could this help you predict accurately the corresponding y value? So somehow if you knew the trend of one stock, you could extract from your line of least squares the trend of the second stock. Well, the answer is your predictions are only as accurate as the strength of the linear regression. And that is given, of course, by the coefficient of correlation. So let us compute this. Now to compute R, we must compute first two additional quantities. The standard deviation for the sample of x values. So we would only take the x values. We have a sample of 6 values. Find the sample standard deviation of those values. Do the same thing for y. And then we can solve for the coefficient of correlation. So let's remember what is the standard deviation for a set of values. So I'll write lowercase s with an x as a subscript to say this is the standard deviation of the x values. If you remember, first we take the variance. So we must sum the difference between each x value and the sample mean x value squared. We divide by the number of values, so n minus 1, but that is the sample variance. The standard deviation, of course, is the square root of the variance. So of course we could compute our sample mean from the definition and the variance from the definition, take the square root, and we have our standard deviation. But if you expand this out and you simplify, you have a shortcut formula that will be given in terms of our summations. And here's what's going to come out of this operation. Let me write the argument first. So it will be the sum of the x's squared individually minus 1 over n, the sum of the x's, the whole summation squared, over, of course, n minus 1. And again, the only difference from here to here is that we've expanded this out and we've simplified a little bit. So the square root of the sum of the x's squared minus 1 over n sum of the x's all squared over n minus 1. And this is now easy as we have everything, right? Square root of sum of the x's squared, that was the result of our third column, 107, minus 1 over n, 1 over 6, sum of the x's squared, this is the result of our first column, 19, over 6 minus 1, which is of course 5. And if you compute this, being a square root will give us a irrational number, but this will be approximately, and here we'll round up again to the 4th decimal place, 3.0605. And now we have our standard deviation for the sample of x values. Well, you can imagine that for the deviation for the sample of y values, it's a copy-paste of this. Change, of course, the x for y. So it'd be the sum of the y's squared minus 1 over n sum of the y's all squared over n minus 1 root of this. So I'll jump ahead. So sum of the y's squared, that was the result of our 4th column, so 112, minus 1 over n, 1 over 6, times the sum of the y's squared. Sum of the y's is the result of our 2nd column, so minus 20 squared, over, of course, n minus 1, which is 5. Let me double check. Good. And if you compute this, you'll find an approximate value rounding up again to the fourth decimal place of 3.0111. And there you have it. So we have the deviation for the sample of x values and for the y values, and now we can find our coefficient of correlation. And there are actually two ways of finding r. The first way, which is now going to be shorter, if we have previously found the slope of our line of least squares. And then I'll show you a second method where we can find r independently of a hat. So here's the first method. If you have found a hat, r is simply going to be the standard deviation for the sample of x values over the standard deviation for the sample of y values, and all of this times the slope of your line of least squares. And we have all three. We have sx, we have sy, and a hat is right here. So if you plug this in the formula, you will find an approximate value for r of, again rounding up to the fourth decimal place, 0.9477. Notice that this is really close to 1, so we have a very strong here correlation. So which means that the points in our scattered plot would lie really close to the line of least squares, which says that the predictions that we can make from the line of least squares should be pretty accurate. Now what if you want to find r independently of the slope of the line of least squares? Well, we have the following formula. So here it is. It is given by the sum of xy minus 1 over n, the sum of the x's times the sum of the y's over n minus 1 times sx times sy. And here we'll leave the calculations up to you, right? We have this sum, we have these two sums, we have n with 6, compute your numerator, denominator 5 times sx times sy, and if you do so, of course, you'll get the same value, approximately 0.9477. And there you have it, how to compute the equation for the line of least squares and the coefficient of correlation using the slope of our line or independently without the slope of our line. Now, if we had a very small value of r, suppose r was 0.02, then we'd have a very weak correlation, a very weak linear relationship between both variables, and we couldn't use the equation for a line of least squares to make predictions. As we have here a fairly strong correlation, we can use our line of least squares to make predictions. So let's do so. So let me remind you of what were our values. And you might ask, well, why? Well, this will be important. So x was negative 1, 1, 2, 4, 6, 7. Y was negative 1, 2, 3, 3, 5, 8. So notice that we've gathered values for x that are always between negative 1 and positive 7, and all our values of y are between negative 1 and positive 8. And we'll see shortly this is important. And we also found that our line of least squares was approximately 0.9324 x plus 0.3808. And we also had a very strong correlation, which again is the only reason why we can justify using the line of least squares to make predictions about x and y values. R was approximately 0.9477. which again is very close to 1. So let's look at an example of what's called interpolation. Inter means in between. You'll see what that means in a second. Suppose that we know the behavior of the first stock for x at a particular time. Suppose we say at that time stock x increased by $5. We may ask then, given this information about x at that particular time, what is the predicted value for y? Well, first thing is, as we gather data for this particular x value, if you look in your table, nowhere have we gathered the data where x was 5. So we don't have it from our table, so we have to go back to our next best option, being the predicted y value from our line of least squares. And it's interpolation because the value x equals 5 is within our range of observed values. We've only have gathered information when x was negative 1 and 7. As 5 is between negative 1 and 7, we're okay here. So we just replaced, right? So y will be approximately 0.9324 times x, which is 5, plus b, 0.3808. And if you calculate this with your calculator, you will find an approximate y value of 5.0428. And that is the predicted y value, given that x was observed to be 5 from our line of least squares. And that is an interpolation, when the x value is within the range of observed x values. What about an extrapolation? Well, if inter means inside, extra means outside. Same question. What if we have an observed value for the first stock x that is $12, and we ask what is the predicted y value given this x value? Can we still use our line of least squares in this particular case? And the answer, if you think about it, is no. And you might ask, well, why? Well, we've only gathered data for x between negative 1 and 7. So all we have right now is evidence of a strong linear relationship between x and y as long as x is between negative 1 and 7. But there is no guarantee that above 7 and below negative 1 that this strong linear relationship still holds. It may break down. It is not because a linear relationship exists between two variables over a certain interval that it does exist forever. And so here, because 12 is outside of our range of x values, the linear relationship could break down, and so we cannot make predictions here. There's nothing we can say with any kind of confidence. So always be wary of extrapolation. And now let's do one last example of an interpolation, but backwards. This will be again an interpolation. But what if now we knew of an observed value for the second stock, at that point they say going up by $4.5, and we'd ask, well, what is then the corresponding predicted x value? Well, once again we use our line of least squares, as our y value 4.5 is within the observed range of y values. So we replace in our equation y, 4.5 is approximately 0.9324x plus 0.3808, and we can now simply solve for x. Subtract on both sides by 0.3808, which gives you approximately 0.9324x, and of course you solve for x by dividing across by 0.9324. And you will find a value of x, if you compute this with your calculator, of approximately 4.4178. And that's it.